Good afternoon, everyone. Before we go into the tutorials, this afternoon we have the drop-in session 5 o'clock, isn't it? 5 o'clock, yeah. So please attend as much as possible, because I don't know, next Monday is a due date. Okay, next Monday is a due date, and if you have any problems or anything, just let me know. How many of you think you should be able to complete?
We have completed beam and slab design, sir.
Beam and slabs, okay, that's good. I think you should be able to do that, columns without much issue. So anyway, we'll discuss that one, so make sure if you have any problems, I'm not sure all teams are there, but if you have friends not here for this tutorial, let them know. If we have any issues or anything, they should attend today's workshop. Okay, if they don't attend the workshops, because I don't take the attendance, but if you have any problems, you need to attend the class, you need to discuss. If you don't attend the class and if you don't discuss any problem and ask extensions, it's not very good. Okay, so please make sure you attend, and I'm happy to support. If you need some 1 or 2 days extra time, should be okay, but that is only for those who attending classes, not a blanket one. Okay, anyway, so let's look at the interaction diagram, and we will see how to design the column. Okay, so for the column design, as we discussed yesterday, first we should have the interaction diagram. Okay, the interaction diagrams are critical for column design. Yesterday we looked at 2 points, gas load and the decompression. Okay, so the difference between the column design and the slab design, we don't have axial load in the slab or beams. In columns we have an axial load. Okay, so technically we draw the cross section area, but the columns, yeah. So columns looks like this. Okay, so it can have bending moment about x-axis and y-axis. Generally y-axis x-axis, or it can be, you can have bending about x-axis or y-axis or both. Okay, I'm talking about one axis at the moment. I'm talking about one axis. So if you have bending about x-axis, then you normally provide reinforcement. And you may have some more reinforcements. Okay, so the dimensions we mark like this. The center to center distance between this reinforcement is marked as a GD. GD, not 9, G. Okay, GD. So the distance from here to there is small d. The distance, this one is the DSC. So this is the standard notation. The small d is the effective length, very similar to the beam from the compression. So this is compression side, this is tension side. Okay, so this is compression side, this is tension side. So from compression side, the centroid of the tensile reinforcement is small d, effective length, and this is DSC. This is the standard notations. Okay, so total steel area is equal to AS area of steel, here we have AST, ASC, compression steel, tensile steel, compression steel, tensile steel. Okay, so tensile reinforcement is AST, compression compressive reinforcement is ASC. So technically this and this are same. Okay, ASC is equal to AST equal to half of that total. Okay, yeah. So yesterday, the first one we look at is cast load in UO, yeah. So no bending. So remember, I am applying an axial force. Okay, I am applying an axial force. So this is the column, yeah, the same column. Okay, scarce load, no bending means you apply the load here. You apply the load here. Okay. Yesterday, this is what I did. I saw this diagram like this. Doesn't matter whether 2 bars or 3 bars, we only look at that area, okay? Whether 2 bars or 3 bars, not a problem. Area of steel, okay? So ASD, this is ASC, yeah? And I apply the load here. So that way in the 2D diagram, but in actually it's a vertical application. Yeah? So this is in UO. Okay, so we look at that one. So here no bending because we apply at the center. Okay. Everything is under compression. Everything is under compression. So we got NUO. Yesterday we got alpha 1 F dash C BD plus FSY minus alpha 1 F dash C AS. We got this one, isn't it? We derived this equation yesterday. Yeah, we derived this equation. No bending, so technically M is equal to 0. Okay, you don't need to tell, but it is 0. Is it correct or different? Same, is it?
Yes.
So we got this one. Remember, if you asked to find out cast load, you are expected to derive that one as we did yesterday. Okay? And we, sorry, I think someone says, so open book or closed book we decided class test?
It's open book, sir.
Open book?
Yeah.
Open book will be different, okay? I will not put
Open book.
open book, okay.
Whatever you put, sir, doesn't matter. We will do open book.
Closed book is too hard.
Okay, yeah. So then you
We
need
need
to,
to-
but no electronic
every-
things. No electronic things, okay?
Yeah.
Open book means everything should be printed or written one. Because electronic
Printed,
one,
sir?
it's very difficult to control the internet and everything. Okay?
Sir, we'll do by writing, yeah, but we need to be in the Zoom facing with the laptops.
Huh?
We need to be on Zoom, yes, sir?
Not Zoom, it's a class test. You need to be here. You need to be in Melbourne campus.
But sir, in the we do for the transportation we used to do in the Zoom, sir.
Yeah, but that is due to COVID.
No, sir. Just recently also we do the in the Zoom, sir, and we used to be in the Zoom and used to be writing.
Is it? I will check with Sakar. I will check with him. My understanding, class test is on campus. That's what
No, we have
for last year.
the
For last year class test for steel and masonry. Steel and masonry, we have a student here, and Sakar was the course coordinator or unit coordinator in Melbourne, and he sent the exam paper I let her sit in a room and she completed in here, not Zoom.
We did, sir, geotechnical exam. We did, sir, in our room, sitting in the room, in the Zoom, facing the Zoom. The camera was 24/7 on, sir, when we was in the
I will double check. It's not my
Yeah.
decision. I will check.
and
with
uploaded the, sir. We uploaded the PDF format
yeah,
of the.
I understand. I also did the exam like that earlier. It's they said that is during the COVID 2020-2021, but 2022 I thought it's back to normal. But anyway, I will double check with Prasad and Sakar. Okay.
Because sir, we don't like the code is not, we can't print the code, and we were not able to print the
Yeah,
AS
you know,
code,
in,
sir.
in
Yeah.
that case, I will tell what other pages you need. At least you should be able to print those pages. Yeah. I will double check anyway. We have time. No problem. Okay. The problem is I need to check with them. I can't decide. Yes, this university tells something, I can't change it. Okay. If university said okay, then I will be okay. Okay. I will talk to Prasad and Sakar. Because Sakar was the course coordinator, unit coordinator for steel and masonry. He conducted on campus. That's what my understanding. I will double check, so don't worry. Okay. So we have 6 weeks to decide. So you want open book, isn't it?
Yeah, open book.
Yeah, that one I can decide. So I will say okay. Okay. So you want open book, isn't it?
Yes, sir.
Yeah. So that one I can say yes. Other one I can't. I don't know. So okay, I will confirm that one next week. Okay. So if you have an exam, if you ask to find out, like a tutorial question, you need to derive that one. No marks will be given if you write this one and substitute. This is 1 minute work, okay? Because all the values are given. Okay, so substitution we don't need. So you need to derive that one. So you need to understand. Okay, so the second one is the decompression point. What this decompression point means? We'll have bending and everything, but extreme tensile fiber will have zero strain. So is this the condition for transportation for this term as well? Huh? Who is doing transportation this term?
Yeah, sir, we are, sir. I'm getting transportation, and the same, we did the same thing with the geotechnical also, and the transportation also same thing.
Geotech is not this term, isn't it? Last term, isn't it? Last year.
Yeah, but the same, but the like we did the exam in the same way, sir.
Okay, I will double check. Because I don't know the situation. Okay, but here, that's what I said. We ran the exam last year. We have a student here in Rocky, Mingna. Yeah, she came to my office. I put her in one room. She completed 3 hours exam over there.
3 hours.
Okay. Anyway, I will double check. I don't know. It may be changed. Okay. Is it class test transportation
Yes, sir.
or online test?
It's a class test, sir.
Okay, I'll check that one. Okay, that's okay. I will double check. I'm not going if that university say okay, I don't have any problem. Yes, otherwise, if yes, the last time. Okay, so this is the decompression point. I think we discussed yesterday, but I just want to make sure it's you understand what actually happening. So this is the center point. So anyone did the steel and masonry last term? No? Anyone did steel and masonry last term, last year, term 2? No? Okay. Yes. I don't know. That is exam. Yes, last year we couldn't run that concrete. We don't have. Okay. Yes, all undergraduates. Yes, for undergraduate students also we had online exam like Zoom we did, but now all are revert back to normal, and they are not class tests. They are sitting in the actual exam hall. So my steel and timber is on 8th of June. So that's the sports venue. So that big exam hall. So that's what I heard from university. Anyway, I'll check that one. Okay. So here in decompression point, when you apply force here, you will not have any bending. That's this case. Yeah. So now we are moving the load to this side. We are moving the load from here. So the decompression we move little bit. For decompression we move a little bit. So we apply the force, the eccentricity, is this one. Okay, so this is vertical force, this is vertical force in UD. So in the diagram yesterday we draw in the 2D view. So this is the middle point. So we apply the load here in UD. So that is the eccentricity. So we have reinforcements here. So this one is a GD. Okay, so this is half GD. This is what we, right? Yeah. Here we have bending moment. So in UD is equal to FC plus FST plus FSC. From concrete, tensile steel, compression steel, everything is under compression. Okay, so the strain, they said the extreme tensile fiber will get zero strain, so the strain distribution looks like this. Okay, so these are the strain distribution. Okay, so those who remember. So here that is 0, so the neutral axis is here. Here these both are parallel, uniform compression. So this will not meet, so the neutral axis will be infinity. Yeah, dn almost very large, infinity, but here dn is equal to capital D. This is the neutral axis. dn is this one, from compression to this one. Okay, so we derive this one, and MUD is equal to E times NUD, the eccentricity, the movement. Okay, so this, due to this, there will be moment. Yeah. Yeah, due to this. So to get the E value, this one is NUD. To get the E value, what to do? Take the moment, about tensile reinforcement. Okay, the reason I am telling again, this is the same work we are going to do for the other one as well. Okay, so only the strain distribution will change, all other works are same. So if you understand one clearly, the rest of the thing is same. Okay, the strain distribution is like this earlier, now it is like this. I'm going to change for the balance point. Okay, clear? So far we completed yesterday. The third point, balance point. Okay, so balance point, so we move the load from the center point. We start to move for decompression somewhere there. Yeah. From here we moved. From here we move towards one side. So decompression somewhere there. So we need to move a little bit further. So somewhere there. Okay. So we apply a force. So that is eccentricity. This is the eccentricity, the new eccentricity. So this is what we are going to analyze. Okay, so I'm going to draw 2D view. You don't need to draw this one in the exam, so just to explain. Okay, so you have the reinforcement, compression reinforcement, tensile reinforcements, and that is the middle point, middle line, and we apply the load here in UB, balance B. So this is the eccentricity which we need to find. So here balance point. What is balance section means? That is a balance section. We discuss in the beams. Over reinforced, under reinforced, balanced. What is balance section? Balance section means the concrete reach the ultimate strain. What is ultimate strain for concrete? 0.003. Okay. When it is reached the ultimate strain, at the same time tensile reinforcement reach the yielding point. Okay. So your strain distribution. So neutral axis, this is not a neutral axis, this is a center point, okay, centroid, okay. So this is the middle of the section, it is not the neutral axis. So neutral axis will be somewhere there. ECU is equal to 0.003. This is the neutral axis. DN and this one strain that will reach 0.0025. Yeah, this one will happen at the same time. Concrete will reach the ultimate strain at the same time the steel reach the yielding point. That is a balance section. Okay, so we'll draw this rectangle. So we have FC and here we'll have a force FSE, compressive force. Now steel is under tension, so we'll have FST. Earlier everything is under tension, now neutral axis is this one. Okay, yeah. For scarce load, neutral axis is at the infinity. At the decompression, neutral axis is here. For balance point, it's here. It's DN is 0.545. We will find out later. Okay. So this is D. So to find out DN, similar triangles, this upon this equal to this upon this. 0.003 upon DN. Okay, this one divided by that equal to this one divided by that. Similar triangle. Okay, so 0.0025 upon this one, D minus DN. Okay, so to solve, if you solve, you know the D, yeah, you know the effective depth. So to solve this one, you can multiple here and there and you can arrange. Otherwise you can add top and bottom. So if you add top, if you add this one, it's a D. If if you consider this and this, you have the answer dn is equal to 0.003 upon 0.0055 times d. Okay. For decompression, what is the dn? Capital D. For balance point, dn is equal to 0.545 small d. So now I will write the equation for Fc. This is alpha to F dash C. This is gamma dn. Yeah. Okay. So stress alpha to F dash C times B times gamma dn, yep, minus ASC, because we need to take that force out, that is a steel. FSC, we need to know whether it's yielding or not. We need to know whether it's yielded or not. Okay, so currently I put FSC times ASC. How to find? That one can be FSY or so E value of the steel is 200 gigapascal. So if the strain, compressive strain, this one is larger than yielding strain, then FSY. If the compressive strain is less than yielding, Hooke's law. How to find out this one? Similar triangles. Similar triangle, this one and this one are similar triangle, ratio should be same.
Yeah.
Okay, so this one 0.003 dn,
Yes.
this one dn minus dsc. This is dsc. Yeah.
Yeah.
So dn minus dsc. So you know the dn is this one. Okay, so then you should be able to calculate. You know the d and dsc. Okay, so you will find out FSC. What about FST? The steel is reached the yielding point, so that is FSY AST. So this is already yielded. Okay, so it's yielding, it's reached the yielding point, so that FSY, you don't need to check, because we already said this is 0.0025, so that's yielding point.
Same way as
Yeah, so that's satisfy this condition. Yeah, so you know in UB balanced one, FC plus FSC minus FST. Why minus? It is opposite. Okay, so this one, this is opposite. so you get them balanced. So you put all the values, then you should be able to get NUB. Okay. Now I need to find out the eccentricity to find out the bending moment. Yeah. To find out the eccentricity, I will take the moment about this point. So this is the resultant force. When you apply this one here, you get this much of force in the concrete, this much of force in the compression steel, this much of force in the tensile steel. So this one is equivalent to this one. Both are same. Okay, equivalent. Okay, so you apply this one, so that cause this much of force. So this should be equal to that. So when you have that one, taking moment about this point here, this one is equal to here. Okay, so first take the moment. So how much this one? ED by 2, isn't it? Yeah. So take the moment, NUB times ED by 2 plus E in plus E equal to take the moment about this one. Okay, so this force will be cancelled out. Yeah, this will be cancelled out. So this and this both are same direction. FSC times this distance, FC times this distance. So I will write FC. I'll write FC times the distance. This distance. From here to there, small d. Yeah? From here to there, small d. This one, gamma dn. So this is half. Yeah? Half gamma dn. So d minus gamma dn by 2 plus FSC d minus DSC, the distance. Okay, so you know all the values. FC you have, yeah, FSC you have, D you know, gamma dn you already have, DSC known, GD is the distance between these two center lines, you know. Okay, if the dimensions are given, you should be able to know. So this is NUB, you already calculated here, so you should be able to find out E. Yeah, you should be able to find out E. So MUB is equal to the eccentricity, so the bending moment about x-axis, bending moment about x-axis is equal to eccentricity times force. Eccentricity is times force in UB times E. So you know in UB, yeah. Okay. So now I have the axial load and bending moment for the balance section. Okay. So in the tutorial, I think you have the solution, isn't it? If you couldn't find that one, just let me know, because I might miss out sometimes. So you have these tutorials. Okay, you have this tutorial. Okay, I work out with all the numbers one by one. In the tutorial I put say NUO like this, but you should derive that one. Okay, so but all other places I work out one by one, say the balance point. I draw this one, yeah, gamma dn. I work out one by one dn and the numbers, and I calculated NUB, and then take the moment about the tensile reinforcement and E value. Okay, E value is there, and using E value you calculated NUB. So full workings are there. Okay, step by step it's written there. Okay, don't read this one, take pen and paper and work out whether you should be able to get same values. Okay, when you read this one it looks easier. Okay, so this is, we are developing the interaction diagram. Okay, we are developing an interaction diagram. That means for a given section, we are changing the steel. So let's say we put the 1% steel, then we are working. We calculate all the points. Then 2% of steel, we calculate all 4 points again. Okay, so that's what we are looking. So currently this is third point. The fourth one is a balanced, the pure bending. The fourth point is the pure bending. No axial load. This is very similar to the beam section. Okay, it is very similar to the beam section. No axial force. So the cross section we have bending only. When you have bending, no axial force, no axial force. Okay, so you'll have a neutral axis. This is not a neutral axis, this is a symmetric axis. Here no axial load, it is very similar to your beam one. So this is dn and this is gamma dn alpha to f dash c fc, the steel reinforcement fsc, and tensile reinforcement FST. Okay, Here we don't know the dn. Here we don't know the dn, but no axial load. No axial load, dn is unknown. Okay. How to find out dn? But definitely dn will be less than the balanced one. Okay, so it will reducing dn. So how to work out? So we'll write an equations. Fc is equal to alpha to f dash c gamma dn times b fst. So this will definitely more than yielding strain because now smaller. So fsy times ast. If you want, you can check it later, but fsc we don't know. This can be either fsy or okay. So we don't know the dn, so similar triangle 0, 0, 3, same equation as we similar things as it is this one. Okay. Only thing is dn is different. So these are the strain for the similar triangles. This one divided by this equal to this one divided by that. Yeah. Similarly, this one divided by this equal to this one divided by that. Okay. But definitely we should know. Definitely yielding. Okay. So normally you can check it, but it will be the case. But for compression we don't know, so that's what we put two things. So now what to do? There is no NUB, so N is equal to 0, no axial load. So what is axial load? FC plus FSC minus FST. Okay, this is the axial load earlier. Look at this one, same format. Okay, same format, but here they said no axial load, it should be 0. Yeah, should be 0. So FC plus FSC equal to FST. So you have to use, you substitute all the values, use this one, this one, this one. Normally this will not yield, so use this one first. Okay, take that one from. So you can find dn okay, and you can check the strains again, whether it's a yielded or not, then moment, take the moment about this point, same point, tensile reinforcement, so you'll get FC d minus gamma dn by 2 plus FSC d minus DSC. Same equation, only different is you have different dn. Okay, so you know the dn already, and substitute, you will get mo. So now you have 4 points. Yeah, so for 1% steel, 2% of steel, 3% of steel, we will find out. We'll find out all 4 points. Okay, so we'll find out technically. Same calculation, only change the area. Okay, we change the area of steel. Yeah, ES value will change. So ES means AST and ASC will increase. So I have the number 1 point. Okay, so this is in U, this is in U. Okay, in U and in U. So you have number 1 in UO, yeah. Then number 2 is here. So NUD and NUD. Third point, balance point, NUB, NUB, that point also there. The last point, MU, last point, pure bend. So we connect them and get the diagram. When you connect, the standard says it should be straight line. It should be straight line. Okay, this is straight line. This one like a curve. Okay, so this is straight line, this is curve. So this is for 1%. Similarly, you can draw the next one. You can have 4 lines actually. Okay, 1% steel, 2%, 3%, 4%. Okay, so this is the balance point. So this is called the axial force versus bending moment. Some textbooks also include pi value. I'll explain that one in a minute, but this is without pi. Okay, you know what is pi? Capacity reduction factor. Yeah, so this is without pi, so you have the graph without graph. So now we will see. Anyone have any problem how to draw this one? You should be able to use Excel for your project to draw this graph if you want. So then it is easier. You have just copy the same thing with the different layers. Okay, only the steel area will change. Okay, all others are exactly same. Okay, so now how to do the design, or how to use this one for the design. So the first one is you apply the load. So let's say you have all this one. So analysis part, I'll come to that one in a minute. Okay. So let's say you have the column. So when you have a building, you apply the load, the flows, and you will analyze this one. Okay, and you will. So we need to design the columns in the ground floor. Okay, we need to look at the columns, not here. So because that will take the largest axial load. So we need to design. So let's assume we have those bending moment axial force diagram. I'll come to that one. If you have any problem, I'll come to that one in a minute. Okay. So now you have bending moment, axial force, shear force, and everything. So first step. Classification of column. So the column classification, give me a second. In section 10, clause number 10.3. 10.3. So 10.3, they said, yesterday I discussed about the buckling effect and others. You remember?
Mm.
So the So you remember this diagram, hopefully, yeah. So this is short column, and that is cylinder column. Okay. So here we'll have the strength failure, no buckling problem, and here the buckling is the main criteria. Okay. So this is buckling area, and this one is a strength failure. So the short column design is easy. Short column design is easier, and that will have better capacity. Okay, short column will have better capacity compared to cylinder columns. So first we need to see whether that's cylinder column or short column. They said column is defined as short column if, so when we can say it is a short column, okay, when we can say a short column, they said unbraced okay. This is what they said. The column, this column or any columns you did considering can be classified or defined as a short column if it satisfies this condition. So if you want to use this condition, you need to know what is braced column, what is unbraced column. First thing, yeah. What is braced column? If you want to use this condition, either this or this is it. So you need to know whether the column is unbraced column or braced column. So let's look at this one. So when you have a lateral load, okay, what will happen? If you apply a force, what will happen? It will sway, yeah? Generally, it will sway. So this point will move. So let's say this point will move here. Yeah. So this is a rigid connection. So the deflected value, deflected shape will look this way. It's 90, okay? Rigid connection means the angle cannot change. go like this. There's this also 90 degree. This is 90, this is 90, okay? So you have something like this, yeah? So this is sway, so the move. But in normal structures, we don't want to have large sways, isn't it? If you have large sway, you'll have very large bending moments. So we'll put some walls, yeah? You put some masonry walls or something, yeah? So what that will do, it will not let this point to move here. So this is cannot move, so this is called sway or unbraced. This is braced. So if these columns are braced, this one also cannot move, because if you want to move, this one need to move, okay? So if you have bracing in one place, you'd be okay. So you can put some walls, something like a shear walls, or you can have some cross bracings. In steel structures, you might see this one, yeah? Some, or even in the concrete, they will put some columns kind of things, okay? So this column will not move, let this part to move horizontally, so this is called bracings, okay? And these walls also can work as a bracings. So if you have these columns braced and other columns also braced, because it cannot move, the whole story cannot move. So this is called braced and unbraced, okay? So if it is unbraced column, the effective length upon R is the radius of gyration, yep. R for rectangular section, so 0.3D, for circular section 0.25D, they said, okay? D is the dimension, diameter or the depth of the section. So you know the effective length for R less than 22, sorry, it is 22, I think. Yeah, sorry, it is 22. It is 22, not 2. So if it is unbraced column, this is kind of a slenderness, okay? If the slenderness is less than 22, that is short column. So this number, this is slenderness, this is P, so this value is 22. If it is less than 22, short column, greater slender column. This is unbraced. For braced column, it is should be less than 25 or the other equation, okay? So we know how to classify the column, that's the first step. So here they give the alpha value, alpha C is given like this, okay? So what is N star? The axial force, okay? So alpha C, they give two values. (2.25) minus 2.5 in star upon pi in UO. or otherwise 1/3.5 n star pi in u UO. Okay, this one is if n star upon pi in UO less than 0.15. This is if n star upon pi in u greater than, oh sorry, this is greater than, this is greater than, this one is less than 0.15. Okay, so that's, you can look at in the standard. Okay, you should be able to look at in the standard. So what is n star? That is axial force. So if you have column, you analyze. I told that you have the axial force, bending moment, and shear force. So this is the maximum axial force in the column, n star. What is NUO? What is NUO?
Neutral.
Slow.
Square load, isn't it? You already calculated. Okay? You already calculated. What is the pi value? .65. I will explain that one in a minute. Pi is 0.65. So we know, I will explain this one in a minute. Okay. So you know n star pi in u. Yeah. You know how to calculate a square load, isn't it?
Yeah.
So you should be able to check whether this or this. So alpha c is okay. 38 is okay. F dash c is okay. The strength of the concrete. So now we have M1 and M2. What is M1 and M2? So when you have a column, axial force diagram will give this one. What is M1 and M2? The bending moment. Okay. So the bending moment M1, M2. Okay, one end is, because you will have two ends, isn't it? For the columns, M1 and M2. So if you look at the M1 and M2, when you have two moments, smaller moment is called M1. So if this one is smaller, you have to put M1 here, M2 there. Okay, M1, M2. Smallest one you have to put as M1. Other one is M2, not top and bottom. Okay, you have two moments at top and bottom. One will be M1, other one will be M2. So they said it's smaller spacer. So, and other than that, they also give some sentence here. Okay, I'm not sure if you have the standard, you can open it. Otherwise, look at this one. Okay, M1 upon M2, the ratio of the smaller to the larger design bending moment at the ends of the columns. That's okay, we know that. What is the rest of the things? The ratio is taken as a negative when the column bends single curvature, positive when bend about double curvature. So what does that means? What is a single curvature, double curvature? So single curvature, when you have bends like this, if you take a ruler and try to bend like this, both are same direction, so this will bend like this. So this is called single curvature. If the bending moment so here I bend this one here and that one this way, okay? So when you bend in opposite direction, okay, so it bends like this. So if you want, you can take the ruler and bends, so it looks like this, okay? So it's a double curvature. So how we know from the bending moment diagram? So when you have bending moment diagram for this one, the bending moment diagram, if you use the softwares, normally the bending moment diagram you can get from the software, they will give a diagram, okay? They will not show the bending moment like this. So normally for this one it will show like this. For this one, the bending moment diagram, looks like this. Okay, so if you have bending moment diagram like this, it's a single curvature. This is double curvature. Okay, so you should know that one when you have the bending moment diagram from the analysis. So here in this case m1 upon m2 become negative number. Okay, so you have the value and take that as a negative. Okay, so if the ratio is 0.2 or 0.5, so it should be, you have to take as a negative point and take that as a negative 0.9, sorry 0.2. So here when you substitute, so let's say this ratio is 0.5, you have to put this as a negative 0.5. Okay, so if the ratio is 0.5, you have to use as a positive. Okay, so this is positive and negatives. That is a positive and negative. But if so if the M2, the maximum moment, M2 is the maximum moment, okay? M2 is the maximum moment. If the maximum moment is larger than, sorry, if the maximum moment is smaller than 0.05 d n star inside the axial lobe, then you have to use the ratio as -1, okay? So what is this one? Why they are talking about this one? This is called minimum moment. Okay, minimum moment. So what does that mean? Why it is important? When you do the designing, you analyze the structure and you get the axial force diagram, bending moment diagram, everything. So when you have that one, when you have all this one, if the bending moments are too small, we should design at least for this moment. This is the minimum moment, okay? If your bending moments are too small in the columns, generally that will be the case in the middle columns, okay? In the buildings, in the middle columns, the bending moment will be very small because it's balanced by the beams. Okay. So the corner columns will have larger bendings, the middle columns will have smaller bendings. So if your bending moments are too small, you have to consider this as a bending moment, minimum moment. Okay, you cannot go more than or less than that. Okay, so now you know all the values. You should be able to classify the column. Is that okay? Yeah. Can you classify whether it's a short column or slender column? This is the condition. You know all the values, how to get that one. Yeah. So if you have a short column, the design is easy. Let's see what to do for the short column. And then we'll go for slender column, okay? So now short columns, now we have, so classify them. So once you have classified, if it is a short column, so we'll use the chart to find out the AS value. Okay, so that means you have these charts. Okay, you develop this one for 1% steel, 2% or 3. So now you have your N values and M values. So you mark that one. Say that is here. This is n star upon pi, sorry, m star upon pi, m star upon pi, and this is n star upon pi. Okay, so you have n star, so and if you know the pi value, you plot that point. So if it is here, you have to provide between 2 and 3. Okay, so you can do the linear interpolation, say around 2.2 should be okay. So you know what is a percentage of steel, so you need to provide 2.2 percentage of area. So you should be able to find out, say for example, if AS is equal to 2.2 percentage, 2.2 times okay, so this number comes from the graph. Okay, from the graph we will get that AS ratio as I explained here. You mark the points. M star, n star is known, so m star upon pi, you mark the point. So if it is between 2 and 3, look at the linear variation, so around 2.2 let's say, so then you should be able to find out AS. So we need to, half the AS will go to compression side, other half will go to tension side. Okay, so that is for the short column. So if you want to design a column, first you need to develop, say you know the size of the column, yeah, 300, 400, 400. So you take the one size of the column and develop the interaction diagram for 1%, 2%, 3%, and 4%. Because minimum 1%, maximum 4%. If you get anything less than 1%, you need to provide 1% of reinforcement. If you get anything more than 4%, you need to provide. You need to change the section. You can't provide more than 4%. Okay, so if you get anything more 4% or more, you should better change the dimension of the column. Maybe you increase from 400 to 500. Okay, but if it is less than 1%, you need to provide 1% still. So first you develop the interaction diagram between M and N. So basically you will find out 4 points for different steel amount, and you develop that graph. Then you classify or you check whether it's short column or slender column. If it is short column, technically you provide the AS obtained from the graph, just plot the values and provide them equally, half on the top, half on the bottom, tension and compression. So that's all you need to do for the short column. Okay, quite straightforward, quite easy if you have all the values. So the question is the pi value. Pi. Okay. So when you look at the pi value, so this is the interaction diagram. This is 0.1, 0.2, 0.3, 0.4, isn't it? Yeah, the gas load, decompression, balanced, and pure bending. Okay, so the pi value, if you look at this balance one, anything above that one, pi is equal to 0.65. Here pi is equal to 0.85, pure bending 0.85. Okay, this is pi is equal to 0.65. So from here to there 0.65, here it will change. The pi value will change from 65 to 85. Okay, there's an equation in section 2. So from here to there, the pi value will change, but anything here, it's 0.65. .65 they said, sorry. Yeah, they said k pi, but k pi normally 1. Okay, they put k pi, but k pi normally 1. If you look at this one, this is the case. Oops. So this is the case, bending with axial compression. Okay, so if n is larger than balance value 0.65 k pi is normally 1. Okay, and if it is less than balance, this equation. Okay, so generally we will get somewhere here for the columns. Okay, most of the columns will end up with 0.65. So we know what to do, how to find out the reinforcement for short column. If it is a slender column, what to do? Okay, we know how to classify the columns, but if it is a slender column, short column is quite straightforward. And what to do for the slender column? So slender column, so we have n star and m1, m2, yeah, the bending moment diagram and axial force diagrams we have. If it is slender column, what we do is we need to multiply the bending moments. We need to multiply the bending moment using a magnification factor, that is moment magnification sigma b for brace column. Sigma S for unbraced, I think. Actually, for the unbraced column, they said check this one, take the larger value, but normally this will be the larger value. Okay, and I read that close 10.4.3. So they said for the unbraced column, check these two values, take the largest, but normally this will be the largest in the cylinder column general. Okay, so that's what I put this one, but if you read the close, you will get the clear idea. So these values are given. This is called moment magnification factor, or moment magnifier. So we multiply using this one, both these bending moments. So if you have moments, then you need to multiply. So we consider larger moment. You multiply by sigma B or sigma S. So we consider a larger moment. Okay. So generally, if it is a short column, we will use these 2 points. But if it is a cylinder column, we will consider a larger value. So when you consider the graphs, we will end up with a larger steel ratio. So if you have bending moment and this is the end arm, so if it is short column, same bending, same axial force, but if it is a cylinder column, it will be multiplied by the moment magnifier. So we will use the larger moment. So we will end up with from here to there. So if, say for example it is 1, 2, 3, 4%. So the initially we have between 1 and 2. Now it is more than 3. We consider larger moment. So these moments will be multiplied by these moment magnifiers. Okay. So the moments so we use the larger moment. Okay, so that is the difference between cylinder and short column. Most of our buildings will end up with the short columns. Normally we don't like the cylinder columns because small variation in the lambda will give a large drop in the capacity. Unless we really need a cylinder due to some limitation, we will normally go with the short column. I think all of your project columns will be short columns. Okay, so your design will be much easier compared to the cylinder. For shear, the standard explain the spacing. I think it's you find out the close number. Yeah, under the section 10.7, read the clause 10.7. They will explain the shear reinforcement. You don't need to do any calculation. They said what is the minimum or maximum spacing you need to provide. Okay, so that is for the shear reinforcement, and this is for the bending and axial load. If you have biaxial, they also give slightly different equation, but still all the processes are like this. Okay, so that is the one we need to discuss for the columns. As I told, these advanced topics will be covered in week 12, okay, week 11 or 12, once we finish the pre-stress. Okay, so that's all for the RC design. And when you work out this project, if you have any problem, you can ask me. I'm happy to help. For the class test, you will have one question in beam, one question in slab, one question in columns. Okay, for RC side. In pre-stress we will discuss later, but for RC, you will have question in beam, column, slab, one from each, plus pre-stress. Okay, so
So,
yep.
So the design philosophy is totally different, sir. What we used to do in our country, sir. Why, sir? But the theory is same, yeah.
But the design.
So the steps and the philosophy is totally different, sir.
I'm not 100%, but it is not totally different. I'm not sure the Indian standard actually, but it is the British standard. It's very similar.
It's totally different, sir. What we used to do in our home country is totally different, sir. Its pattern is totally different, sir. Design pattern.
So you don't do like this one for beams and slab?
No, sir.
Okay.
We don't used to do like this, sir. We used to calculate the bending moments and shear force, but we don't used to do these kinds of things, sir.
So how you design? How to determine the steel ratio?
So we have prepared the Excel sheet. Just put the value. The design sheets automatically comes, sir.
Yeah. So who create the Excel sheet? They will
Sir,
provide.
by us, but sir, I actually like every step. I don't know, but we used to calculate we used to check the dimension of the beam, and then we used to calculate the reinforcement directly, sir.
There are some work Excel sheets. So the companies here, if you work, they develop Excel sheets, Excel workbooks. So, but this is the background theory how to develop the Excel sheet.
Yeah, sir. But how we used to design, sir, it's totally different in bachelor and this masters over Australia.
Oh, okay. Yeah, maybe it's because I'm not 100% sure about the Indian standard, but I'm from Sri Lanka. We use the British standard VS 8110. That is not exactly same, but more or less same.
Yeah, sir. But the code is different. The values should be different, sir. But the design steps and procedures should be
because in India and Sri Lanka we use cubic strength.
Yeah.
Okay, here cylindrical strength. So the strength wise different, so the values will be different in the equations. So the approach more or less, even if you look at that one, I think they try to link, try to align with the American standard.
Yeah, sir. Definitely, sir. They like Indian standard is like more of carried from the American standards.
So here also they